In this video, we're going to talk about the basics of computer vision. So computer vision has a lot of applications for robotics. Like you might want a robot to be able to open up your fridge and see what's inside of it. You might want your robot to be able to look at the world around it and see what people are doing and what the other objects in the environment are. And most importantly, you want your robot to know the difference between a cat and a dog. So how do we do this? Well, first off, let's talk about what is a camera. So let's say you have something in the real world you would like to record, like my cat Cricket here, and you want to store it. You want to store it as something that's portable, something you can post on the internet, something that you can manipulate, something you can put in presentations, whatever it is, you want to be able to store it. So how do we do this? Well, we all know that there's some material out there that reacts to light. We can call that photosensitive material. So what happens if we just hold up a piece of photosensitive material to this scene on the left here? What happens if we do that? Well, the light from the reality over here will hit the photosensitive material, cause some sort of a reaction, and you might get an image out of it. Unfortunately, light doesn't really work that way. Light spreads out. So each point on the right-hand side here experiences light from multiple points in the real world. And what this means is you're just going to end up with a really blurry mess that's just faded out and completely worthless. So what do we do here? Well, we need some way to limit the amount of light that gets the material. We need to limit it so that only a little bit of light from the real world gets to each spot in the material. So you're only getting a little tiny sample of one tiny spot in the real world for each spot in the material. We can do this by limiting the size of the area the light can travel through from between the real world and the photosensitive material. And in this way, we limit it so that a very, very small amount of light can get from the real world to the photosensitive material, and we end up projecting the image from the real world onto the photosensitive material. And this is called an aperture, this little thing that limits the amount of light that gets through. So what we've just invented here is a pinhole camera. Pinhole cameras were used by artists way back in the day to be able to paint landscape images photorealistically by taking a room, putting a little hole in the wall in the room, and allowing the light from the landscape to get into the room like that. Early cameras used this as well and put chemically reactive material on the other side there to capture the image, and it worked okay. So the pros here is the image is perfectly proportional and flat. And we're going to get into flat a little bit more when we talk about camera calibration in another video or two. But this is also really simple to build and operate. There's no moving parts, just a hole in the wall, and you place it however big you want the object to be in the image on the wall behind you. The cons here is that this requires a lot of space. We can't have this much space in our robots. We can't have this much space in our cell phones when we're trying to put a camera on them. So this clearly isn't going to scale. And also, the amount of light that you let in is directly related to how blurry the image is. If you remember earlier, the more light we let in, the more washed out the image becomes, the more blurry the image becomes, the less useful it is. So we'd really like a way to control those through two separate knobs. So how else can we do this? Well, we can use a lens. A lens is a piece of curved glass that we put in front of the aperture so that we can direct the light coming in a more focused way. So similar to a pinhole camera, this will limit the amount of light from the real world that gets to each spot on the photosensitive material. Unlike a pinhole camera, we can actually control the distance between the lens, the distance from the object, by how we construct the lens. And each lens has what's called a focal length, which relates the ratio between the distance from the lens to the object and the distance from the lens to the sensor, so that you can design your camera to work in any situation. So the pros here are that we can put the sensor much, much closer to the aperture than in a pinhole camera. We can also adjust the light independently of focus, mostly. There's some caveats to that. It's also relatively easy to make a lot of different types of focal lengths, so you can make a lens for just about any application you need. There's still a few cons. The focal length is usually fixed for a given lens. You can get around that by using multiple lenses, but for the most part, we keep them fixed. The lens also unfortunately distorts the image, and any imperfections of the lens, because of course it's a process where you make glass, so imperfections will get into the uh, piece of hardware, it'll distort the image even further. We can account for that, and we'll talk about that a little bit later. Two common types of distortion are barrel distortion here, where it looks like the thing is bowed towards you, and pincushion distortion, where it goes the opposite direction there. And again, we'll talk about this some more when we get to calibration. So we've talked about this photosensitive material that you can take pictures with, but we haven't really gone into detail with it. And most of those details belong in a different class. We're going to talk just a little bit about one type of camera sensor called a charge coupled device here. And this is basically what the type of camera that's in your phone, your laptop, anywhere else that you're going to be using a camera. In the modern day, it's usually a charge coupled device or something very similar. So how does this work? Well, you have this scene in the real world. The scene in the real world is then focused by a lens, which then goes into this charge coupled device, which is a two-dimensional grid of transistors. And each transistor is reactive to the light that gets in and returns a charge based on the amount of light that got into it, and then that gets filtered out to the computing device that's connected to it so that you can get an image out of it. So this lens focuses the image onto the CCD. You end up closing a shutter and save an image based on what was stored in the charge coupled device after the shutter was closed. So we figured out how we can possibly get images from the real world. How do we represent these images in code? Well, let's first think about an individual pixel. So what does one thing in this charge coupled device return? What does one transistor return? Well, in our code, it returns a value from 0 to 255, where 0 is no light received, and 255 is maximum amount of light received. And if we take that and make a two-dimensional array, like these people have created here, then we can see on the left-hand side is a very, very low resolution picture of Lincoln. In the middle image, someone has taken that picture and put the exact value, pixel value of each of the pixels onto the image. So you can see in a grid there what the values would be from 0, which is dark black, to 255, bright white. So every image you see is composed of numbers just like this, usually from 0 to 255, although that sometimes depends based on the library we use. So that's great, but how do we represent color with this? We talked about how to do black and white images, but how do we actually get color out of it? Well, it turns out you get color by filtering the light coming into each of those pixels with what's called a Bayer filter. And a Bayer filter is this two-dimensional filter put on top of a CCD, where you have blue spots, green spots, and red spots. And each of these squares you see in the image here corresponds to one pixel on the camera. So if you're paying attention, that means that each 4-pixel square here becomes 1 pixel in the final color image. So how does this work? Well, each of these pixels in the filter will take in the blue light, let's say, in the top left corner there, and filter it so only the blue component of the image is received by the CCD below. The green component will take only the green component of the light coming in, filter down to the CCD below, and so on across the image. You'll notice there are twice as many greens as there are blues and reds. This is partly because it makes a nice pattern, and also partly because that's how the human eye tends to see things. We tend to be a little bit more sensitive towards green, so it mimics how we see the world, which may or may not be how we want robots to see the world, but it's a good starting point. So in this way, we can say each of the pixels we saw beforehand that was just a black and white image on the two-dimensional screen, we now have another dimension to think about. So when we're representing color images, we have this two-dimensional array in the front that represents the width and the height of the image, just like we think about it, and then a third dimension that extends off orthogonal to those with the red component, the green component, and the blue component. And that's how we get images from the real world into code. In our next video, we'll talk a little bit more about how we actually manipulate these using OpenCV library and how we can get that into ROS so we can play with it with the robot.